Hello, everyone. My name is Jared Longfox at the University of Central Florida and Brown University. I am one of the hosts of the AIAA Space Resources webinar series that you are attending. This webinar series is uh, organized and hosted by the Education and Outreach Subcommittee of the Space Resources Technical Committee of the American Institute of Aeronautics and Astronautics, AIAA. Our mission is to uh, get the community, all of us professionals, as well as general enthusiasts from around the nation, around the world, talking about space resources, space exploration, the cutting edge ongoing work that is going on around the world, as well as what's coming up next. And today, we are lucky enough to have Dr. Ian Jen from the Colorado School of Mines here to talk to us. I'll let him introduce himself in just a minute, but a couple of last parting notes for me before I hand it over. I need to enable closed captioning. I don't know if that enables it for you, but there we go. This will be a recorded webinar, so if you have any friends, enemies, whoever that can't actually make this in real time, there will be a YouTube video posted with this recording within the next couple of days after this talk. I just put in the chat the link to the YouTube channel where you'll be able to find it. And I need to dig this link up. I thought I had it ready. I don't right now. But I'll also post in the chat a bit later the link to the repository where we post the slides from these from these webinars. So look out for that. As for those of you who have attended, you'll know that we do a Q&A at the end of this, so please access that little Q&A question mark speech bubble at the bottom. Put in any questions you have, and we'll get to them in the order received after Ian is done presenting. Um, Other than that, I think I've covered it all. Ian, sorry for taking so much of the time. Please take it away. I'll be in the background here if you need anything.
Great. Thanks, Jared. Appreciate it. Let me share my screen here. Yes, thanks for joining. Yeah, my name is Ian Jen. I am currently an adjunct professor at Colorado School of Mines. My research focuses on regolith and foundation interaction, particularly for lunar surface construction. Before I came back to academia, I was working in the civil and structural engineering world. I am both a licensed civil engineer and a licensed structural engineer. I have about 12 years of terrestrial construction experience, and now I'm trying to apply all that to applications for lunar surfaces, particularly for landing pads, which we're going to talk about today. So yeah, I wanted to kind of present what is the foundation engineering philosophy for the lunar surface, specifically for landing pads. So yeah, I'm just going to get right into it here. Just a quick introduction onto what foundation engineering is, particularly lunar foundation engineering. These slides are going to be kind of a summary of a publication that I put out last year in Acta Astronautica. I have that listed here with a link. Again, Jared's going to share these slides if you guys are interested in reading this publication. But lunar foundation engineering kind of is a combination of 5 different things. There's some planetary science involved, understanding the geology of the environment, and then a lot of ISRU. How do we build landing pads utilizing resources that we find on the lunar surface? And then obviously the lunar surface itself as a resource to support the foundation. And then there's the traditional geotechnical and structural engineering of the foundation approach, engineering the regolith itself below the foundation and then engineering the actual foundation itself. And then obviously with all construction projects, there's an aspect of quality control and characterization, just making sure that things are constructed the way that we need them to be in order to perform the way we designed the design intent itself. So I'm going to quickly start off here just with a quick review of lunar regolith itself. I know there's probably a lot of people on this call that are pretty familiar with regolith, specifically lunar regolith, but it is something that requires an understanding so you can understand the behavior. So the lunar regolith is the moon's surface consists of this soil-like dry fragmented granular material. This is what we call regolith. The difference between terrestrial soils and lunar regolith is the irregularly shaped particles. The morphology is very different than what we see terrestrially. And then they also have some variations in diameter, but it does tend to fall within the well-graded sandy silt, the way that we see on Earth. There's two main areas of the lunar surface that we have characterized different regoliths. There's the Mare regolith and the Highlands regolith. These basically boil down to both elevation differences and some mineralogical differences. So the highland regolith is what I'm going to be focusing on. That's the white areas of the lunar surface. This is where all Artemis missions are currently planned to go to highlands regions on the South Pole. So that's kind of where we're focusing on that. But there is some differences between the two regolith classes. So I just wanted to note that. The big part of regolith and why it is so different from terrestrial soils is its formation process. So this video is just kind of indicating all of the craters on the lunar surface that are less than 1 billion years old, just kind of highlighting kind of the level of impacting that occurs on the lunar surface and why this is important for regolith formation itself. The various meteoroids that are impacting the surface create a kind of this overturning and mixing process that we do impact gardening. And this is why the lunar surface has a little bit more homogeneity than we see from terrestrial soils. To kind of go into this a little bit more, when these high velocity impactors hit the surface, they create these ejecta curtains that kind of deposit regolith in the surrounding area of the crater. And this is kind of where this turning comes in. So there's this constant reworking of this surface. So you get this really fine powder on the immediate surface of the moon. And if we're going to build anything on that, we kind of need to understand how that regolith is going to perform from a granular mechanics standpoint. This isn't the only mechanism for regolith formation. Like I said, there's the meteoroid impacts and the meteoroid impact gardening, but there's also space weathering that occurs from the exposure to solar and cosmic radiation, and then that can alter some mechanical properties. But there's also thermal fatigue, which are the fluctuations between the day-night cycles on the lunar surface, and that can create these stress gradients that can fracture these particles. And then we also have a component of electrostatic charging, and that's that fine regolith particles that can acquire this charge and then influence particle movement and things like that. The figure on the left is a stratigraphy of the lunar surface itself. We have this immediate surface of regolith that is fine grained, reworked and deposited. And that's supported by kind of like an area of large scale ejecta. So you're going to start seeing larger rocks and things like that below that. And then there's the structurally disturbed crust supporting that large scale ejecta and eventually a fractured crust. This is important just from transferring forces down from the immediate surface of the moon down into these various zones of regolith. And finally, I just wanted to kind of show some examples of what these regolith particles look like. Regolith comes in a bunch of different types, but there's just a lot of irregularity is what I kind of wanted to point out. There is some spherical particles. You can see that impact glass sphere. So that's actually when an impact occurs, there's so much energy into that event that it actually melts some of that material, and as it's being transported across the surface, it turns into a sphere and then is deposited that way. But most regolith particles tend to be regularly shaped with these sharp morphologies. And then the immediate surface that's kind of affected by the electrostatic and radiation are these fairy castle structures that are like the immediate surface of the regolith. You get these create like interesting matrix type particles that have these really small, fine things that can crush really easily. So the next important part when it comes to regolith is understanding its density state and how density is related to particle packing and things like that. So the top right or top left figure is a difference between a poorly graded and well graded, or in geologic terms, a sorted and poorly sorted material or granular material. So the lunar regolith tends to be, let me use my laser pointer here, that tends to be well graded, which is the one shown in B here. This is basically the particle size distribution is shown on this figure on the bottom left, which shows the range of particle sizes. And this is from the lunar source book, plus or minus 1 standard deviation from carrier. Just shows you what from the Apollo samples that were taken, specifically for the Highland regolith, what that kind of distribution looks like from a particle size standpoint. The last thing I wanted to mention on this slide was the density, in situ natural density profile that has been determined from various missions to the lunar surface. So that's this figure on the right here with this red dashed line. The big thing I wanted to mention here was the way the regolith forms and it is deposited, you quickly get a density profile where you have high density packing of the regolith particles at a relatively shallow depth. So this bottom or this top axis is the relative density. That's the comparison of the actual density to the maximum density state that the regolith can get to. So you can see that this red line, right around 20 centimeters, you're getting up to 90% relative density. So it gets dense very quickly. So it's really that top 20 centimeters of depth that has this kind of fluffier and less dense material, which is important from a foundation standpoint, and you'll see why here in a few slides. Okay, so to get into the foundation engineering philosophy, we need to talk about the Mohr-Coulomb failure relationship, and this is basically a measure of strength or how much the regolith can support. And when it comes to granular material, this is a relationship of shear strength, basically the shearing of the regolith particles against each other. So the big part of the Mohr-Coulomb failure relationship is that if you have a denser granular material, you're going to have a stronger strength. This should be pretty inherent in everyone's mind, but in practice, a lot of people don't really see the relationship between density and strength. But this is a direct correlation utilizing two major geotechnical parameters, what we call cohesion of the soil and the internal friction angle. And so that's in this relationship here, as tau is the shear strength of the soil itself. So this is the idealized version of the Mohr-Coulomb failure relationship, but if you were to take a bunch of triaxial tests to determine those geotechnical values, you would actually see that the Mohr-Coulomb failure envelope is actually curved in nature. Basically, there's a relationship where you can only get so much strength with so much density. So the linear Mohr-Coulomb failure relationship is the typical model that we use, but in practice, you will see this curvature and you'll have a change in internal friction angle with density. The cohesion is just the intercept on the shear stress axis, and that will also be related to that actual curvature itself. A really good example of this, and Jared was actually a co-author on this publication, to show that this density change correlates to a shear strength, is this figure right here. This is the cohesion and shear strength of compacted lunar and Martian regolith simulants. But the big thing here is as you increase in density on this axis, you get an increase in strength. And then also, if you alter that normal stress at all, you'll get a little bit difference in that strength. But ultimately, higher density, higher shear strength. So before we get into the foundation approach, I just wanted to quickly summarize a few different geotechnical properties for both the Mare and Highland regions of the regolith itself. What I have here is just kind of a summary of these values from known science missions to the lunar surface. This includes the Apollo missions, but it also includes some of the newer missions that have gone to the Highlands regions. But I have listed here the minimum and maximum densities, and then the cohesion and friction angle. But I also wanted to include something called the compression index. And the compression index basically quantifies the deformability of a soil when it's subjected to an increased effective vertical stress. So this is basically a measure of deformability, and this is important for foundations, and you'll see why in the next slide. And then also just to further define cohesion and friction angle, cohesion is the intermolecular forces between the soil particles. And then friction angle represents the actual shear friction interaction between the particles. Okay, now that we've covered the regolith, let's talk about foundations. So before we go further, I want to define what a foundation is. I don't know how many civils are in this call. I'm going to assume it's none because that tends to be my experience in the space industry. I'm the only civil out here screaming about regolith and why it's important and things like that. So we're going to start with what is a foundation? So the definition of a foundation is a structural element that connects a superstructure to the ground. So I've drawn kind of an idealized version of this. The superstructure is this top component, and this is the foundation itself. The purpose of a foundation is to distribute any loads applied to the superstructure over a larger area, of the foundation. And this is to reduce both the deformation and pressure resulting on the ground. So if you have these applied vertical and horizontal loads on the superstructure, that's going to transfer down into the foundation, and you're going to have this resulting ground pressure in this trapezoidal shape. And then we have this delta here, which is the actual deformation down into the surface. So depending on what system you're developing that this foundation is going to support, you need to make sure that that deformation is understood so that your system can basically account for that vertical movement downwards. And then obviously resulting ground pressure, we go into things like bearing capacity and things like that, which is completely related to the shear strength of the regolith itself. There's one more component of foundations, and this is to prevent lateral movements of the superstructure. And this can be done through overturning resistance or anchoring. Not something I'm going to talk about too much here, but lateral forces on the moon exist. Seismic activity exist. I think we've already heard from Dr. Nirma Kaluk about this, talking about seismic activity. She is my co-investigator on all our seismic work. But yeah, so it's important to think about lateral forces. But for this example that I'm going to show you, we're only focusing on forces that are induced from a rocket landing on the surface. Okay, the big part here, though, is I wanted to compare the difference between a traditional foundation and how that relates to landing pad foundations. And this is simply the fact that your superstructure goes from something that would be, similar to like a column in a traditional building to the actual lander itself. So the lander, it has become the superstructure, and it transfers forces, vertical and horizontal forces, through the lander legs that then bear on this flat slab surface foundation. So just to idealize what this means, actually I have two slides mixed up here. I'm going to go to this next one first. If we were to idealize a landing pad foundation, we have a rocket sitting on this large flat concrete slab, or sintered regolith is what I'm calling it in this figure. But it's an engineered surface that then transfers those vertical loads through the surface at some point, and then that is going to transfer those loads down into some sort of prepared regolith subgrade. And we're going to talk about that preparation as part of the foundation engineering approach. And then that is to transfer all those forces down into the regolith subgrade below. So going back to the slide that I mixed up, if we were to model the flat slab of a lunar landing pad, that would be something like this. We have a foundation, a flat slab foundation here with an applied load, and then we can model the subgrade below as a granular material with a stiffness. And I'm pretty sure everybody in here is familiar with stiffness, but just to further define it, stiffness is basically your applied force divided by the resulting displacement. So you can model the regolith as a series of springs that are going to compress as you apply load, and that compression is basically a rearrangement of the various particles and things like that. So sorry for the mix-up on the slides here, but let's start with the displacement component of this stiffness equation. So when it comes to displacement of a granular material, and in terrestrial geotechnical engineering, we call this settlement, which is basically, like I said, the rearrangement and densification of particles. There's kind of three main components of settlement that need to be incorporated. And this is for traditional foundation engineering. The first one is this green SI, which is going to be permanent deformation or plastic or particle crushing or distortion. So especially with that fairy castle structure on that immediate surface, this is going to be the crushing of those particles and filling the voids that were created between them. And then this is so this is a plastic deformation, and agglutinates are actually a good component of this as well, where it can fracture these kind of weaker particles. The bigger component of the settlement is going to be this one in blue, which is consolidation settlement. This is the actual rearrangement and densification of particles. Utilizing some traditional soil mechanics approaches, this can be modeled utilizing this equation, which is basically the total change in void ratio by the applied load divided by 1 plus the original void ratio. And void ratio, I'm going to show here in a few slides how you quantify that, but that's where that compressibility index comes in. And then finally, for terrestrial soils, we have something called secondary compression. And this is what's shown in red here. This is time-dependent densification that occurs typically in saturated soils. So this is soils with water ingrained in the matrix. We are likely not going to have this type of soil on the lunar surface. The big thing I want to note here is this does occur in permafrost soils. So if we were to build any type of foundation in permanently shadowed regions where we might encounter icy regolith, this will be something that needs to be accounted for in the total regolith surface displacement equation. Moving on to the force component of that stiffness equation. This is basically the bearing capacity failure. So this is generally listed as three different types of shear failure. The one listed in green is what we would typically see in high density soils. So this is when you're applying a vertical force down, you get these failure wedges that occur where the soil is actually starting to push outward and upwards, and you're getting these bulges on each side of this actual vertical component. So this is the type of failure that we want to see in foundations. This is a high strength failure. But if you get down into this yellow, this is considered local shear failure, where you start having much more jagged failure on the load versus settlement plot. These tend to be showing yielding closer to the edges of the footing and often occur often are accompanied by these kind of quick jerking movements when you're applying that load. And then finally, in the red, we have a low density failure, and this is called punching shear failure. This is considerable vertical settlement that occurs immediately as you apply that load. So this is the things that we see when we're looking at the Apollo boot print photos. The Apollo lander foot pads as they touch down to the ground. We have large deformations that occur very quickly, and that's because of that low density immediate surface. And then, yeah, like I was saying, this ultimately goes into ultimate bearing capacity. This is a bearing capacity plot that I think people are pretty familiar from the Lunar Sourcebook. I'm not going to talk about bearing capacity a whole lot because settlement tends to be the bigger issue that we need to deal with when it comes to lunar foundation engineering. The only reason I'm including it here is simply because the bearing capacity of regolith is very, very high on the lunar surface because of that formation mechanism where we get that very high density regolith at very shallow distances from the surface. So we're not going to be building anything that is going to exceed bearing capacity on the lunar surface anytime soon. It is something that we need to consider eventually. Once we get our first high rise on the South Pole, then we're going to be talking about bearing capacity a lot. But immediately we need to just focus on maintaining and mitigating surface settlement and deformation. Okay, so just to summarize everything I've talked about from the foundation engineering approach, if we were to design a lunar landing pad foundation on the South Pole of the Moon, we need to think about two things. We need to reduce the surface deformation and reduce the applied pressure of the surface. But like I said, that applied pressure is not as much of a problem as the reducing the surface deformation part. So to reduce surface deformation, we can utilize two different approaches. One is we can densify that immediate surface to get to a higher density state so that we won't see any type of rearrangement and consolidation of the regolith below when we apply that foundation and the loading on that foundation. Or we can simply excavate down to that natural high density subgrade, which was shown in that density plot. Getting down to 20 centimeters will get us considerably more dense regolith, requiring much less actual surface preparation before we construct the foundation on top of it. If we were needed to reduce the applied surface on to the applied pressure on the surface, you can do that by basically engineering your foundation a little bit better. This is either by reducing the applied loading, which doesn't necessarily or can't necessarily occur all the time, but you can increase the loaded area onto that surface, and that's simply by increasing the foundation size, making it wider, thicker, things like that. So that would be the structural engineering approach to reducing that applied pressure. So if we were to take a scoop of lunar regolith and kind of look at it from a pure material standpoint, you can make something called a phase diagram. And this is simply grouping all the solids and then all the voids. So if you were to take a scoop of regolith, you can quantify how much actual solid mass is there and the voids between them, utilizing kind of what we're calling this phase diagram. And this is where you get the volume of voids to volume of solids, which is that void ratio that I mentioned earlier. But this is kind of how you quantify the actual density state. The reason I'm bringing up phase diagrams here is just to show you this single slide so you can kind of see a visual representation of what this means. So if we were to take in situ non-compacted regolith on the left, we have some component of voids and some component of solid regolith. But as we increase the relative density, I have 60, 70, 80, and 90% relative density, you're just decreasing the voids between it. And obviously this creates a higher density. So the reason I'm showing 90% density here is this is kind of a number that's been thrown all around a lot, especially when it comes to lunar surface preparation. 90% relative density is the standard minimum density state that is required for all terrestrial construction projects through the International Building Code. So this is why 90% is used right now. You're going to see in this presentation that I'm going to tell you that that is something that we need to think about and not directly compare to the lunar surface, because lunar regolith does not behave the same way that a saturated soil on Earth supporting that same foundation would behave. So I also have listed here on this figure two other values. The second value is the actual density at that percent relative density. So 60% relative density is 1.48 grams per cubic centimeter, and then 90 is 1.79. And then I also, this value on the bottom is the distance from the surface down to that where the regolith gets to that natural state. And so we had that curve that showed that sharp incline. That's going to be very interesting when we're comparing 80% relative density to 90. 80% relative density occurs naturally at about 6.7 centimeters below the surface versus 90%, which is 19.9 centimeters. So if we wanted to prepare our surface simply to 80% relative density, we're looking at probably just excavating down 7 centimeters and being done with it, versus if we needed to get to 90, we have much more to do, much more energy to put into the system, much more surface preparation we need to think about. So keep this in mind as we go into the actual landing pad design, because this was going to be important when we're thinking about surface preparation. Okay, so if we're going to design a landing pad, I have shown here, this is from Icon and Big. I think these images have kind of been shown around a lot, but we're thinking about some sort of flat slab engineered surface that is going to receive landing and launching vehicles. Just to summarize why it's important to think about landing pads like this is vertical takeoff and vertical landing operations. So this is, I think we're all familiar with how SpaceX has been doing things, landing vertically. This is how Artemis 3 is going to land, and all the preceding Artemis missions. But we have basically the plume environment is created because the rocket nozzle is oriented at the bottom of this landing vehicle, and that high plume environment can create what is called plume surface interaction. And these are these plume high velocity and high heat plumes that are interacting with that regolith, and that regolith is very low density, so you can create high particle or high velocity ejecta regolith particles that can reach ballistic trajectories and travel long distances in vacuum. And this is obviously a very dusty and dangerous environment. So if you're landing anywhere near other mission assets, you're going to have these regolith ejectas, and it's going to be a big issue. So we want to make sure that we mitigate this plume surface interaction utilizing a landing pad surface. And this is the landing pad itself is going to create stability for the landing zone, and then also actually create that load transfer down into the regolith surface to support that lander so that it lands perfectly vertical. We don't have any overturning or tipping issues. We actually had a pretty good, and hopefully this video shows through with my bandwidth, but we had a pretty good example of this regolith ejecta from Firefly last year, where you can see this huge dust environment occurring, and you can actually see, there was a pretty good size regolith, a rock that kind of was ejected out of there as it landed, but you get this pretty intense dusty environment. And this is a very, lightweight lander compared to what we're talking about when it comes to HLS vehicles. So it's something that we really need to consider for HLS, because interacting with the surface with much higher velocity, higher pressure, and higher heat flux from these HLS landers is going to basically make this problem exceedingly worse. We have pretty good examples of when SpaceX, this is the Falcon Heavy boosters landing on a concrete landing pad terrestrially. You can see the amount of debris that's occurring. This is from Everyday Astronauts film. They had a camera set up during that landing back in 2018. But you have a lot of debris blowing around. And, when you don't have an actual atmosphere to interact with, this is going to create this same problem. The big thing when it comes to actual the plume environment is how much pressure and how much heat flux is generated. So this figure on the top right is a CFD model that shows kind of a rocket nozzle and the resulting pressure out of that nozzle and the result at the interaction horizontal surface below. So there's an 11-ton lander and a 40-ton lander here. You can see the large increase in the stress topography or the pressure topography here. But this is something, this concentrated pressure here occurs because of something called the stagnation bubble. So when you have this vertical rocket nozzle blowing, this pressure and heat flux down, you can create these almost eddying type things where you have a concentration of this pressure and heat flux. And then you have the component of vertical pressure and then also plume shear pressure on each side. So in that publication that I mentioned at the beginning, which is where most of this work comes from, I kind of go through this process of simplifying these loading values, specifically pressure and heat flux from a chemical rocket propulsion system. The reason I'm doing this is because every rocket manufacturer does not want to share data from their rocket or from their rocket nozzle itself. It's an extremely proprietary area, so they don't want to share any estimated pressures or heat flux. So I went through and kind of proposed this very simplified estimate, and I want to really reinforce this, that I'm not claiming that these values are exactly one-to-one. There's so much variability in this thing. These are only used for approximations only, so that we can design a landing pad. But to simplify this just into 3 simple steps, and if you're curious how I did this, please refer to my publication. But you determine the total energy output from the rocket nozzle, and from that you can calculate the plume heat flux and the plume pressure immediately outside that nozzle. And then, like I said, due to that stagnation bubble, the order of magnitude of that pressure and heat flux immediately outside the bubble tends to be the same at the maximum point that that nozzle is interacting with that horizontal surface. Um, from there, I'm utilizing something called a bullseye landing loading geometry. If we were to look at an actual CFD model here on the left at various elevations, 7, 5, 3, and 1 meter above as that rocket is landing and interacting with that surface, you can see that we have this concentration of pressure in the center. So I propose this bullseye loading to basically simplify that loading and making sure that we're accounting for any type of variability, and the maximum plume pressure and heat flux is in the center, and then that dissipates as you move outwards from the centroid of the plume itself. Again, a few ways of quantifying that here, more in the publication if you care to learn about it. But the bigger thing here is estimating the maximum plume pressure and heat flux for our landing pad design utilizing different vehicle classes. So just based on vehicle mass and resulting rocket engines that were used that are used for each of these masses, I've kind of summarized a maximum plume pressure and heat flux for different vehicle classes. I have light, medium, and heavy CLPS landers, and then light, medium, heavy HLS. And then also I've listed ultra heavy HLS, which is Starship HLS, and then the resulting plume pressures and heat fluxes. These values are, if anyone is familiar with the American Society of Civil Engineers, we're putting together a lunar construction guidelines document. We're going to be talking about it a lot more during this year's Earth and Space conference in April. But these estimated plume pressures and heat flux values are going to be a chapter in that document so that the industry can kind of utilize an approximated approach for landing pad design. So in order to design the landing pad itself, I utilized a finite element analysis here, kind of a traditional structural engineering approach, just as an example in this publication. So I'm utilizing the 500,000 kilogram HLS lander, which I listed as a medium HLS. And then we're assuming a monolithic sintered regolith pad of about 40 meters in diameter. So this gray element is the actual landing pad itself, and that is supported on about 3 meters of compacted regolith subgrade. And so this is regolith that is compacted and densified past that in situ state. And I specifically picked 3 density states that I'll show here in a minute. What I have shown here is 90% relative density, but I'll go into that in a second. But I just wanted to show basically my meshing approach, how I modeled the 2 different elements, the regolith in green and the pad in gray. You can see there's a concentration of mesh in the center there that is to basically account for that high plume surface interaction with that pressure and heat flux, and making sure that the model is distributing those stresses correctly. So yeah, so we have the lander coming down. What I'm presenting here is just the landing event. The launch event will obviously have different environments. There's going to be that rocket nozzle is actually going to be closer to the surface with that interaction. The bigger thing, the reason I'm showing landing here is because it's typical in vertical takeoff, vertical landing operations that as that lander comes down, there's going to be an engine cutoff at some point, and then that lander is going to free fall the rest of the way and impact that surface. So I wanted to account for the impacting event of everything centered on one leg so that we can see what that does from a structural engineering standpoint of the landing pad itself. So we're going to go into the loading conditions real quick. This is I generated based on my bullseye approach, I generated a loading point plot that I used for both the plume pressure on the left here and heat flux on the right, just showing that distribution from the center. That was then imported into ANSYS to create the actual loading geometry. But you can see the maximum values I used here for both pressure and heat flux. And then I utilized a time step approach where I assumed the landing event occurred over 4 seconds. And as you can see, like for example, on the vertical pressure, the pressure increases up to that maximum pressure at 4 seconds, and then we have an engine cutoff at 5 seconds. So I'm assuming the impacting event from one leg occurs at 5 seconds, and that's where you get this kilopascal, 423 kilopascals of one leg hitting that surface. And then after that impact occurs, we have statically the lander statically bearing on that surface. Last thing to show you before I actually show you some failure modes is the material properties that I used for this design. I don't need to go into these very in depth here, but I have pad material properties listed in this table below, and then regolith material properties listed here. Big thing here is I'm utilizing 70 and 80 and 90% relative density, and that corresponds to different geotechnical values per that density state, like I talked about at the beginning. Big thing here, modulus of subgrade reaction. Those are those spring constants. So you have a higher stiffness with denser regolith. So we're going to look at how much deformation occurs from that landing pad down into that regolith surface utilizing these three density states. The identified failure modes that I have listed in that publication, I'm just going to quickly review here. When it comes to the landing pad itself, we need to consider three main structural failure modes: axial, shear, and bending failure. Axial failure occurs, physical crushing of the pad. Shear failure would be an actual punching failure of that lander leg hitting that surface, kind of punching out this trapezoidal wedge. And then there's bending failure, where you have compression and tension couples in a flat slab, so you get bending in the slab. If your tensile capacity is exceeded by the actual tensile stresses, you will get crack development on the tension side of this bending element. And if those tension stresses end up being very high, those cracks can propagate all the way through and create this crushing and breakout failure of that top surface. This is very typical in concrete design. And since sintered regolith is a brittle material or non-ductile material similar to sintered regolith, it's a good kind of failure mode to identify. And then that bending will be directly related to how much settlement occurs below that pad. So if you have more deformation of the subgrade below, you're going to have more bending of the pad. There's also some surface failures that we need to just consider. This is more of a serviceability or maintenance thing we need to think about when it comes to landing pads. We know the Morpheus lander showed some pretty good examples of this, but you can have cracking or chipping of that top surface, or because of this high temperature environment from that heat flux, you can get delamination and eventually spallation of the immediate surface, where you have these large stress differentials. And then you can get surface erosion or ablation from that spallation. So that's just actually removing this material. And this was from the Morpheus landing. After 10 landing attempts, you can see that concrete would spalled and eroded off pretty good. And then these circles are actually chipping marks from the lander legs itself. If you do end up getting plume pressure down through like cracks in the pad, you can get a pressure buildup and have actually this excavation of the surface. So that's just a failure mode to consider. I assume a purely monolithic pad in my example, but it is something to make sure that we consider when it comes to landing pad design. Okay, let's just quickly get into this. I got about 5 minutes left. So I have shown here, I've separated the plume pressure and the heat flux into two different loading events, and then we're going to combine them into an envelope at the end. These are just exaggerated deformations. The important thing I want to mention here is if we're just looking at plume pressure interacting with this horizontal surface, you're getting a downward deformation of that pad material into the regolith surface. But if we're looking at just heat flux, we're increasing that temperature, and then that pad material is going to expand, and so it expands upwards and outwards. So the deformation from a structural analysis standpoint is you're fighting between plume pressure putting down and temperature pushing up. So you're going to kind of see at the end, our overall deformation is decreased because of that. Quickly reviewing what the resulting surface temperature was from this landing event, you can kind of see in the section view here how much the temperature changed. I did fail to mention that this was a 1 meter thick pad. I realize that's a very thick pad. I'll talk about that here at the end. But that was the thickness of the pad. So you can see that it does transfer a good amount of heat, or at least temperature change, down into that 1 meter thickness. So the thinner your pad is, the more you're going to see a temperature change. But ultimately, we saw a temperature change of about 27 degrees Celsius through this landing event. The heat flux itself created some compressive and tensile stresses, and then a maximum upward deflection. So the compressive stress was about 37 or 371 kilopascals, and the tensile stresses on the top surface were about 41 kilopascals. And then we saw that upward um, deflection of about 2-4 millimeters. If we're looking at the plume pressure, we're going to have opposite. We have compressive stresses on the top of 365 kilopascals, tensile stresses on the bottom surface of 395 kilopascals, and then a downward deflection of 1.19 millimeters. I'm sorry, I'm going pretty fast to these last ones. If you are curious about these, please look at my publication. These figures are much larger and easier to see. Anyway, back to this. The last, there's two more loading events. There's that single leg impact, and I have the deformation shown in section here. This was just a single leg load. We actually had a compression and tension couple of about 5.37 kilopascals, so much lower than we saw from the plume event. But we did get a 0.22 millimeter downward deflection, and that's not that's an eccentric deflection. You can see the actual rotation of the pad occurring and the resulting regolith below. And then, when we're statically bearing, we have a uniform deflection, much less overall compressive and tensile stresses. So really the governing loading case is the plume event itself. And then we obviously see much more sustained downward deflection in the pad. So if we were to envelope all these into one, we got, maximum compressive stress of 365, maximum tensile stress on the bottom surface of 395, and then a maximum downward deflection of about 1 millimeter from the plume and 0.22 millimeters from the leg impact. Again, this is a 1 millimeter thick pad, and the compressive and tensile stresses were not exceeded based on that assumed material properties of the pad itself. So we don't have any cracking. If you were to decrease the thickness of the pad, you're absolutely going to start seeing cracking and tension. And then there's also going to be some thermal shock that would need to be accounted for because of that thinner pad. And then obviously repeated launch and landing events will develop those fatigue issues that I was mentioning from the, shown in that Morpheus lander figure. So expansion joints could probably mitigate this. This was a monolithic pad itself, so it's not something that we need to really talk about right now. Last thing I wanted to mention here was our various compaction states. So this is the last slide. I wanted to show how much settlement occurred between the 70, 80, and 90% relative density states. I have the actual sections shown here, but they're kind of difficult to see the difference here, so I have them listed in the table. But you can see the difference between 70% relative density, the settlement that was experienced, versus 90% relative density is 0.05 millimeters. So when we're thinking about preparing the surface, 0.5 millimeters in settlement can easily be handled by the foundation design itself. But that is a considerable amount of energy input into the preparation of that pad surface. Again, we're looking at 4.3 centimeters versus 19.9 centimeters. So do we need to have 90% relative density supporting our landing pad? In my opinion, absolutely not. It's a waste of energy and it's a waste of money sending up a rover to prepare that surface. So it's something that really needs to be talked about in the community, that this 90% relative density rule that we use terrestrially is not apples to apples for the lunar surface, and we can likely handle most of that settlement just by engineering our foundation systems a little smarter. And with this, it's really 0.05 millimeters is nothing. So that was my big soapbox climax here. I will end it here and open up for questions. I have a QR code if you need to contact me, that can get you my email address and anything like that. But besides that, yeah, I welcome any questions.
Awesome talk, Ian. I personally have several, but we have more in the chat.
Okay,
We'll
great.
address those first. Nithyoga Goswami says, "You are not alone. I am a geotechnical engineer from Langen Engineering. I am so happy that you have brought foundation design principles to the space industry, folks." Which, yeah, same. Does electrostatic charge affect the Moore Coulomb strength criteria? If so, how does it affect the strength of lunar regolith?
Yeah, there is some talk right now about how we want to quantify cohesion and the electrostatic charging or spacing on the actual uh, part of interparticle bonding there. But yeah, do we need to include electrostatic charging in cohesion? I personally think that we should use cohesion as a overall envelope for anything that's interparticle connecting. But that is a larger question that is occurring in the industry for sure.
And for what it's worth, I do agree. And I've seen papers recently where they do investigate the effects of electrostatic contributions to regolith overall to bulk regolith strength. And it's there. It's not gonna like double your strength or anything, but
Yeah.
it's not something to be neglected. To back what Ian said.
Yeah, and it is something that changes with the day-night cycles too. So
Yeah,
it's something
exactly.
that we do need to account for. But in worst case, if you're designing a foundation of the worst case thing, that's you would want to assume that those connections aren't there so that you have less shear strength from it.
Yeah,
Yeah.
yeah, true, true, exactly. Thank you. Next question. Andrea Rodoloni says, "I think moon landing and liftoff of SpaceX should use the same model as the Ghost lander. What do you think about G equals 1.62 newtons per kilogram?"
Okay, I will just say that I am very concerned with Starship landing on the lunar surface. Without any type of mitigation, surface mitigation. I know that they're working on utilizing or orientating their rocket or their nozzles higher up on the rocket itself to kind of mitigate this plume surface interaction, but those lander legs still are going to be putting a lot of force down onto an unprepared regolith surface, and there's massive potential for deflection there. So I agree that the model's the same. The Blue Ghost and Starship are going to have the same type of operations and the same type of interactions with their lander legs and everything like that. So I think that answered that question. I'm not sure.
I think so.
Yeah.
Same person says, "I think the Blue Moon lander is ideal as the moon to gateway material transfer model by refuel Blue Moon around the moon, substituting fuel tanks." Thank you for
Yeah, I
the
agree.
yeah. Perfect. Nithyoga Goswami says, was that a fully coupled thermomechanical analysis, referring to, I assume, what is your FEM?
Yes, yeah, it was both the structural mechanical stress and thermal analysis that poured anyone who's familiar with ANSYS within the workbench, we had both the thermal and the mechanical.
I'm not an ANSYS user, I'm an Abacus user, but
Sure,
yeah,
yeah.
yeah. um, anyway, Matt Engel says, "Hi, Dr. Jen. I don't think I count as a civil engineer in the audience yet, but maybe someday." Anyway, question.
Great.
What might need to be done to mitigate crater what might need to be done to the mitigate craters found on the surface of the regolith as part of the work to prepare a foundation to be placed on its surface? Or, given the tiny difference in deflection on your landing pads, would superficial craters need to be mitigated at all?
Yeah, that is a good question because the crater itself has a very different density state. So if you were to infill craters to create kind of, cut and fill, make sure that you get a flat surface to receive the landing pad, you want to make sure that those craters are at least going to match that same density state so you don't get differential settlement issues because that's the bigger part. If you don't want like kind of a weak part in your landing pad where it can deform easier and then you're going to have major cracking potential from that differential settlement. So it is important to think about craters and making sure those craters match the density profile of everything surrounding that crater.
Well said. Um, Rakesh Khan says, "Can you please speak a bit about pad levelness tolerance and the risks of differential settlement, my goodness, and eccentric landing?"
Yeah, eccentric landing. Okay, I'm going to do eccentric landing first. That's a bigger problem when it comes to the shear strength of the pad, especially if you get a lander leg that touches like right at the edge of the pad. You have overall less shear capacity, and that's where punching shear can be a problem. Um, so yeah, and then obviously if you had your pad modeled as the monolithic pad like I did, you can have the differential settlement problems because one side of the pad's not going to receive any load and one is going to be concentrated. So the landing envelope or the precision landing and things like that is going to be important. That's why I think there's a lot of talk about these really large oval shaped pads um, that can kind of handle this type of variability in the landing zone. So yeah, it is something we need to talk about. And obviously my model was very simplified, just trying to get kind of the process or the conversation going in the industry. And then I did touch on differential settlement a little bit in that last question. But yeah, there's definitely potential for differential settlement. And we can't assume anything's going to be uniform and working exactly eccentric or yeah, not in concentric. So
Perfect.
yeah.
Thank you, Ian. We do have several questions still in the chat. I am going to freeze them here. We are going to continue, but all the questions in the chat are right now are the ones we're going to take. Sorry, anybody else who had any questions, you can reach out to Ian after. So to continue on, Alan Whittington asks, "What was the maximum temperature you calculated in the stagnation bubble?"
Oh, I'd have to actually go back and look. I don't think I have those in the slides itself. Yeah, that would be something that my publication would. I just don't have it off the top of my head. Sorry.
No problem. No problem. James Green says, "Who would build the pad?"
Yeah, that's a good question. It'd be nice if rovers could do it. It's a pretty big structural element that we're putting on the lunar surface, so it does seem like it would need a little bit some pretty intense autonomous construction rovers. Um, but I've worked in the construction industry and I know how efficient throwing a bunch of human beings at something can make. So I'm kind of a big proponent of sending a construction crew up there, but that's just me.
Well put.
Yeah.
Carlos Aguilar Boristeros, pardon that. Hi, Ian. Wonderful presentation. Thank you. In your opinion, are current commercial lunar regolith simulants good enough or distributed in enough volume to support all the testing and research needed to develop structures on Earth before we try and build them on the moon?
Yeah. Um, yeah, this is a whole nother seminar.
Uh-huh.
Do I think we have simulants that adequately represent the surface? No, I think they have very specific applications, geotechnical simulants, mineralogical simulants, things like that. Um, we try and do our best, but we are not getting one-to-one right now, and I don't think that we will anytime soon. It's very difficult to mimic the exact particle size distribution and morphology that we've received, especially from the Apollo samples.
Yeah. Our labs spend a lot of time thinking about this. This is
Yeah,
what keeps us up at night,
it's a
everybody.
big question for sure.
All right. Thank you. Nicholas Palumbo says you talked about temperature gradient reaching 1 meter in depth in the pad from your heat flux applied. I'm curious about your assumptions for the amount of time the heat flux is applied for a given landing and the thermal conductivity of the landing pad material.
Yeah. The thermal conductivity was just assumed from various publications of sintered regolith simulants themselves. So that's where that came from. And then, yeah, I assumed 4 seconds basically of heat flux exposure that increases heat flux as the lander was descending. So it's basically 4 total seconds of heat exposure that got that 23 or whatever degree difference in or temperature change.
That's significant over the low thermal conductivities
Yeah, and
of geomaterials.
yeah, and that's why thermal shock is definitely something.
Yeah.
And I did fail to mention I assumed daytime conditions that it was landing. So if you were landing at night, you'd even have higher changes for like significant changes and things like that. So it's going to be important, especially for maintenance of the pad to make sure that the pad is as hot as it can get before we land this really hot plume environment onto it.
Makes sense. All right, this is the last one I said we'd take, but we're making good time through these. I'm going to extend. Ian, do you have time for two more after this if we
Yeah.
make them quick?
Yep. Sounds good.
Okay. Anonymous attendee says, what additional research or test missions could be done to reduce the risks in construction of a large-scale landing pad shown in your model? Great question.
Yeah, that is a good question. It would be, it's a question that completely relates to funding and how much money we're willing to send to the moon before we, put down heavier landers. It would be very nice to have some sort of scaled test. It'd be cool if we had like a small scale landing pad and a CLIPS lander with all kinds of sensors on that pad so that we can get some very good direct data to show how much pressure and heat flux that it actually sees, especially in the vacuum environment. Um, that would be if we had all the money in the world, that's what I'd be doing, trying to get tests going with CLIPS landers and eventually, you know, work up to Starship instead of going straight to Starship. You know what I mean?
Well put.
Yep.
Andrea Rotoloni says, "What is the tech-tribology readiness level of actual extraction machines?"
Oh, I don't know if I know the answer to that. To extract to make centered regolith, I assume.
I think we can operate under that assumption for the sake of
Yeah,
this.
that
Yes.
obvious. I don't think, there's a lot of work. Icon particularly has been doing a lot of centered regolith work. I couldn't really comment on what their TR level is currently, but I know that they have put a lot of energy into making a system that uses a concentrated energy laser sintering system to do this sort of thing.
Um, just for the sake of answering the question,
Yeah.
I haven't seen a specific TRL published for for specific sintering technologies, but general ballpark. Some of them are nearing four around the fours and fives. I expect to see some TRL 6 like flight ready demo payloads within the next couple of years
Hmm.
from those like Icon. My group here at UCF does a little bit of that. I
Right,
know
right.
Mines does launch too, so we're
Yeah.
working on it.
Yeah, it's coming along.
And the last one from Tomasha Dodge. Hi, Ian. For Starship HLS, a 6 centimeter differential settlement is structurally manageable, but geometrically significant due to the vehicle's height. So I'd like to see how much settlement you would actually accept to still be able to unload the payload.
Yeah, and that's a good question. And this has to do with the vehicle manufacturer themselves. They're going to have tolerances within, they'll have things within their legs to adjust for tilt and things like that. So that we can probably account for some bit of settlement just within the lander itself, which could be helped. But obviously, if we're going to build a pad to be utilized over and over again, we want to make sure that we have very low chance of actual differential settlement and making sure that it maintains that same elevation across the whole pad. But yeah, I think when it comes to landers themselves, it's going to be on the manufacturer to specify that tilt tolerance and things like that.
Well said. And we are a few minutes over. Apologies, everyone. Thank you all for the great discussion, though. Quick note before we sign off here, in the chat to everyone who's still here, I did put a link to the AIAA Engage page. It's where we post the slides from these webinars that we're able to anyway. You do need an AIAA account, but you do not need to be an AIAA member. It is free to access these with a free account. If you have any questions, please reach out. The link is in the chat, and I'd happy to send it separate. I also reposted the link to the YouTube channel where these talks, including this one, will be uploaded. Ian, thank you so much for a great talk. I know I said it before we officially started the webinar, but I'm always really glad to have a bit more focus on the ground side of our future in lunar permanence. I thought your talk was great, and based on the conversation here, I think others agree. I appreciate your time and contribution to this series
Oh
and the
yeah,
field.
absolutely. Yeah, thanks for inviting me. I'm glad that we could talk. If anybody has more questions, feel free to reach out to me.
Sounds great. Thank you all for your support of this webinar series. I'm Jared Longfox, and we'll see you next month. Bye, everyone, and thanks again, Ian.
Yep. Bye, everyone.
Bye.